Alright, this is paper 1 of mock 2. Question 1. A solid substance is placed in a flask. The flask is gently heated and the temperature of the substance is recorded at regular time intervals. The diagram shows a graph of temperature against time. At which point does the flask contain both a solid and a liquid? So this is basically a heating curve. We have the temperature in the y-axis and the time in the x-axis. So a heating curve will have multiple sections. Some will be sloped upwards and some will be horizontal, or basically they'll have a gradient of 0. So the regions where the temperature is increasing, for example, this section, this one is just showing an increase in temperature. And note that we started with a solid, so in this stage, this is still a solid. Then from this part, the horizontal part that we have over here, this part represents state change. We know that during state change, there is no temperature change, or you can say temperature change is equals to 0. So during state change, both states are present at the same time. So in this case, since we are heating a solid, we know that a solid will melt, and as it melts, it will form a liquid. So from this horizontal section, we will be able to observe both a solid and a liquid. So that means the answer should be B, but what about the other sections? From the horizontal part to the next upward sloping part, this again represents an increase in temperature, but this time, since the state change has been completed, this is a liquid. So a liquid's temperature is increasing. And finally, the last section, the last horizontal section, this is again a state change. So again, the temperature change is 0, but this time the state change is from liquid to gas. Basically, this is boiling. So in that case, we will be able to see both a liquid and a gas at that stage, but since the question asks when it's a solid and liquid, so the answer should be B for the first one. Moving on, data about two compounds is given. The compounds are H2S and PCl3. We have their melting points and boiling points, and it's said that they're placed in a bottle close together at a temperature of 90 degrees Celsius, and we have 1 gram samples of both of them, PCl3 and H2S. A detector is placed in the container 2 meters away from the two bottles. The two bottles are opened at the same time, and now they're asking us which row is correct. Compound that reaches detector first. So first of all, let's determine their states at 90 degrees Celsius. So state at 90 degrees Celsius. So let's look at H2S. Its boiling point is minus 61. So obviously at 90 degrees Celsius, since it's much higher, it must be a gas. Similarly for PCl3, again, its boiling point is 76, but our temperature is 90 degrees. So again, this is also a gas. Now, we know that gases diffuse faster than liquids. That is a fact. But over here, both of them are gases. So we can't really make a comparison based on whether it's a gas or a liquid. So the options, if you look, that say that gases diffuse faster than liquids, those are automatically irrelevant because both of them are gases. So then how do we make the comparison? The factors affecting diffusion are mainly two things. The first one is temperature, which in this case is the same for both of them since both of them are at 90 degrees Celsius, but the other one is molecular mass. So molecular mass, if you were to calculate for H2S and PCl3, we can immediately just by observation say that PCl3 will have the greater mass. And the reason being that there is 3 chlorine atoms, whereas H2S only has 1 sulfur atom. So obviously PCl3 will have the greater mass. But if you want to, you can still calculate just by doing 35.3 times 35.5 times 3, you will get a mass that's bigger than 32 plus 2. So the later part isn't even required. So PCl3 has the greater mass. So as we know, if something has more mass, it will obviously travel slower. Now you might raise the question that, all right, in this question, they stated that both of them are 1 gram samples. Now, yes, that is correct. However, when particles are traveling, they're not traveling as one complete unit. It's not like 1 gram entirely is traveling. Rather, the individual particles are traveling by themselves. One particle traveling doesn't depend on the other particle traveling. One particle's mass will only affect that particle itself. Over here, 1 gram would simply affect the moles of each particle present, and moles would in turn affect number of particles, which is again not relevant for diffusion. So in this case, since PCl3 has the greater mass, it will diffuse slower, and since it's diffusing slower, that indicates that it will reach the detector later. So because of that, we can say that H2S will be the one that reaches the detector faster or first, and it is because because H2S has a lower MR than PCl3. So the answer for this one is B. Moving on to question number 3. This is pretty straightforward. W is ethene, X is air, Y is iodine, and Z is brass. Which row is correct? So over here we have to identify which one is an element, which one is a compound, and which one is a mixture. So brass is an alloy, of copper and zinc. And we know that alloys are always mixtures. They are mixtures of metals and sometimes non-metals. So since it's a mixture, that's one part we have already identified. And then iodine is an element. It's it's I in the periodic table, and it exists as a molecule of I2. And even if it exists as a molecule of I2, it's still considered an element. Do not think that it's a compound. And then X is air, and air is a mixture of gases, namely nitrogen, oxygen, carbon dioxide, and many more gases. And W is ethene. Ethene, which is C2H4, is definitely an organic compound. So now that we have identified all of them, it's pretty easy to determine which one is the answer. So the element over here was Y, and the compound was just W. So in that case, since D is the only one with both of them correct, we can immediately say D is our answer. Moving on to question number 4, the letters X, Y, Z represent different atoms. So we can see that X has 19 protons, Y has 19 protons, but their mass numbers are different, or the nuclear numbers are different. That indicates that these are isotopes, because they are the same proton number but different mass number. Z, on the other hand, has 20 protons, so that's completely different from the other two, so different element. So now if you look at our options or in the question itself, which statement is correct? So since we already figured out that X and Y are isotopes, that definitely means that the first one is correct. X and Y are the same element. So now if you look at B, X and Z are the same element. That's wrong. They're different because of their different proton numbers. And then X has more protons than Y. They have the same proton number, as we have already found out. Z has more neutrons than Y. So for Z, if we calculate the number of neutrons, that's 40 minus 20 equals to 20. For Y, it's 39 minus 19, which is also equals to 20. So again, that is wrong. Moving on to question number 5, which diagram shows a section of the ionic lattice of sodium chloride. So ionic lattice of sodium chloride will consist of Na plus and Cl minus ions bonded together. Now we know that like charges will repel, so it's not possible to have Na plus attracting, or Cl minus and another Cl minus attracting each other to form a bond. So in that case, if in our structure we see anything similar to that, then that pretty much means that's wrong. So if you look at our answer options, in the first one, we have Na plus bonded with a Cl minus in every direction. So that pretty much indicates that A must be correct. But what's wrong with the other one? If you look at B, Na plus and Na plus are bonded. Cl minus and Cl minus are bonded. Both of them are not correct. And then if you look at C, it's Na minus. Na is a positive ion, it's a cation. All group 1 metal ions are cations. So that means Na minus is not correct. And for D, it's again the same issue. They used Na minus instead of Na plus. So the answer should be A for question number 5. Moving on to question number 6. 4 statements about graphite, diamond, and silicon 4 oxide are listed. So the first one, diamond and silicon oxide are both very hard and have similar structures. That is true because they are giant molecular structures. So the first one is fine. In diamond, each carbon atom is joined to 4 other carbon atoms. This is also fine because of the fact that diamond has a tetrahedral structure. In number 3, silicon 4 oxide forms a giant structure of silicon and oxygen atoms. That is also true. Silicon oxide is SiO2. We have silicon bonded with oxygen in this structure. And there are more oxygens in this direction as well. So 3 is also fine. And then 4, diamond and graphite both conduct electricity because they're both forms of carbon. This is not a correct statement. Graphite is the only one that conducts electricity due to its mobile electrons. Diamond doesn't have any mobile electrons. So in that case, number 4 is a wrong statement. In that case, we can say that 1, 2, and 3 are correct. So the answer for this one is A. Moving on to question number 7, which row shows a pair of molecules where the MR of compound is exactly half that of compound Y. So you can serially calculate each and every MR over here and you eventually get to your answer. So for example, if you were to calculate for CO2, that would be 12 plus 2 times 16, that adds up to 44. And then if you do the same for CH3, CH2 and CH3, that's 12 times 3, and then we have 8 hydrogens, so that's plus 8. So 12 times 3 is 36 and 8 would give you 44. So over here it's not half, it's equal. Now let's just jump to D. Usually for these long calculations, what I suggest is check the first one, check the last one, and if you get the 2 answers from there, then that's fine. It's just a way of getting the correct answer in a quicker way. So again, we know for CO2 it's 44. This would be helpful because we already calculated that before. And for this one, the other compound, if you were to calculate CH3, CO2 and C2H5, we have 4 carbons, so that's 4 times 12. The number of hydrogens in this case would be 8, and we have 2 oxygens, so that's plus 2 times 16. If you were to calculate this, we would get 88. And since 44 is half of 88, it fulfills the requirement of the question. In that case, the answer for here should be D. Alright, moving on to question number 8. Compound Y is the only substance formed when 500 cm cube of ammonia reacts with 250 cm cube of carbon dioxide. All measurements are at RTP. What is the formula of Y? Over here, the main concept that we need is volume ratio is equals to the mole ratio in the balanced equation. This is the main concept that we need for this question. Once we know this, the rest of the question is pretty straightforward. So over here, ammonia is reacting with carbon dioxide and we have their volume. So for ammonia it's 500, for carbon dioxide it's 250. So we can see that if you simplify, the mole ratio is 2:1. So in that case, if we form the reactant side of our equation, it's 2NH3 plus CO2 to form an unknown compound Y that we are not sure of. But we can identify what element is present in what amounts. So for nitrogen, we have 2 nitrogen, or if you write it in this way, we have 2 nitrogen atoms. And then for hydrogen, it should be 2 times 3, so that's 6. For carbon, that's just 1. And for oxygen, that's 2. So out of these options, whichever one fulfills these requirements of having 2 nitrogen, 6 hydrogen, 1 carbon and 2 oxygen should be our answer in this question. So if we were to analyze and check, the first one has 8 hydrogen, so that doesn't work. The second one, it has 6 hydrogen, it has 2 nitrogen, it has only 1 carbon and 2 oxygen. So B should be our answer. Let's look what's wrong with the other one. C, if you look at the hydrogen, there's only 4 of it. And for D, there's 8 hydrogen again. So this is again wrong. Moving on to question number, this should be number 9. The equation shows the production of iron by the reduction of iron 3 oxide. 80 tons of iron 3 oxide produces 50 tons of iron. What is the percentage yield? Now, a lot of students get confused when they see tons or megatons or kilograms or some other mass unit other than grams. But the thing is, at the end of the day, the only difference between grams and tons is the fact that it's being multiplied by a certain power of 10. But once we do the calculations, eventually the powers do cancel out, so you don't have to worry about tons, especially for a percentage yield question, because percentage yield, if we recall, percentage yield is equals to the experimental mass divided by the theoretical mass. The experimental mass is often called the actual mass, the one that we have obtained, and times 100, because obviously it's a percentage. So since it's divided, the powers get cancelled out, so we need not worry about whether it's tons, megatons, kilograms. We can just consider them to be grams. Alright, so 80 tons of iron 3 oxide produces 50 tons of iron. So let's find out the moles of iron 3 oxide present. So moles of Fe2O3 would be 80 mass divided by mR. So mR of Fe2O3 would be 56 times 2 plus 3 times 16. If we perform this calculation, we should be getting, let me just quickly solve it, 0.5. So this is the moles of Fe2O3. So now if you look at the molar ratio of Fe2O3 and Fe, it's a 1:2 ratio. In that case, moles of Fe should be double of Fe2O3. So it should be 0.5 times 2, that's 1 mole. So now 1 mole of iron will definitely have a mass equal to its atomic mass, which is 56. But how much did we obtain? We obtained 50. So in that case, percentage yield should be 50, the actual mass, divided by 56, the theoretical mass, times 100. And if we do that, just by observation, we can immediately determine that it's going to be 89, because think about it. If it's 68 or 63, then it would be closer to half of 56. But over here, this is significantly closer to 56, so that means it must be 80%. It's just an observation. You don't really have to worry about it. You can calculate it. No one's stopping you. All right. This one should be question 10. Which reaction would produce the greatest volume of carbon dioxide at room temperature and pressure? So we have multiple reactions over here. We'll have to go serially to check which one gets us to the answer. So burning 1 gram of carbon in excess oxygen. So let's find out the moles of carbon, because if you have the moles of carbon, we can then use the molar ratio of 1:1 to find out the moles of carbon dioxide and then find out the volume of carbon dioxide. So if you were to do that, the moles of carbon would be 1/12. So mole is equals to 1/12, and since the molar ratio is 1:1, in that case the mole of carbon dioxide is also 1/12. Now over here, I won't calculate the volume, mainly because if there is more moles of a compound, then obviously we will have more volume of that compound as well, because at the end of the day, volume is simply moles times 24, a constant. So if moles is higher, volume will also be higher. So in B, it's saying thermal decomposition of 10 grams of calcium carbonate in the air. So again, the molar ratio is 1:1. So let's find out the moles of 10 grams of calcium carbonate. So they already gave us the MR of calcium carbonate, very generous of them. So 10 by 100, which simplifies to 1 by 10. And we know that 1 by 10 must be greater than 1 by 12. So at the moment, B is the answer. Let's check. So adding 10 grams of sodium carbonate to an excess of dilute hydrochloric acid. So 10 grams of sodium carbonate. Again, it's the same process for this question. We find out the moles of the substance and then moles of carbon dioxide. So 10 grams of Na2CO3 would be 10 by 106. Now we can immediately compare these two and determine that 10 by 100 is obviously the greater value, so we need not worry about this or worry about simplifying this. And lastly, adding 50 cm cube of 1 mole per dm cube sulfuric acid to an excess of copper carbonate. So 50 cm cube of 1 mole per dm cube sulfuric acid. We know that moles equals to concentration times volume when it's a solution. So the concentration over here is concentration over here is 1 mole per dm cube, and the volume is 50 cm cube. Now since it's dm cube, we need to convert the cm cube, and that is done by dividing by 100. So now if we simplify this, that's basically 50 by 1000. Again, it's going to be a quantity that's smaller than 1 by 10, because this simplifies to 1 by 20. In that case, we can conclude that B must be our answer. Moving on to question number 10, 3 compounds are listed: copper 2 nitrate, zinc sulfate, sodium thiosulfate. Which row shows the element that is present in the greatest percentage by mass in each compound? And again, they've generously given us the molecular masses of each compound, or in this case, the formula masses of each compound. So for copper 2 nitrate, it's a comparison between copper and oxygen. If we check, we have 6 atoms of oxygen over here. So let's calculate for oxygen. So 6 times 16 divided by 188 and times 100 for percentage. So once we calculate this, 6 times 16 divided by 100, we obtain, 188, we obtain 51% approximately. Now in a compound, obviously only one substance can occupy more than 50%. So that means oxygen must be the one with greater percentage compared to copper. So we don't even have to calculate copper. Now the same process for zinc sulfate. In zinc sulfate, again, we see that there's 4 oxygen but 1 zinc. But look at our options. The ones that have oxygen for copper to nitrate have zinc for both. So we don't have to look at zinc sulfate. Rather, we have to look at sodium thiosulfate. In sodium thiosulfate, it's a comparison between sodium and sulfur. However, let's try to make this a bit more efficient. We have 2 atoms of sodium and 2 atoms of sulfur. Now, obviously, sulfur will have the greater mass. Now, why is that the case? Because sulfur has an atomic mass of 32, sodium has an atomic mass of 23. Obviously, 32 will always be greater than 23, regardless of whether you multiply it by 2 or 3 or 4. So since we have same number of atoms for both of them, since sulfur has the greater atomic mass, it must, as a result, also have a greater percentage mass in sodium thiosulfate. So in that case, sulfur is the answer. So that means D is the answer for this question. Moving on to question number 12. Aqueous copper to sulfate is electrolyzed with copper electrodes. That means it's an active electrolysis, where my electrodes are participating in the electrolysis process. What is the equation for the reaction occurring at the anode? At the anode, the copper will lose electrons to form Cu2 plus ion, and the 2 electrons. In that case, the answer should be A. And since copper is losing electrons, we can say that this is an oxidation reaction. Moving on to question number 13. Hydrogen reacts with chlorine to form hydrogen chloride. We have the reaction provided. The enthalpy change for this reaction can be calculated using bond energies. And whenever we want to calculate enthalpy change using bond energies, the formula is del H is equals to bond energy of reactants minus bond energy of products. Let me just write it in short. So bond energy of reactants minus products. Now, why is this the case? Because we want to break the bonds of the reactants. So that's the endothermic part. And then when the products form the bonds, energy is released. So that's the exothermic part. So this is the endo, and this would be the exo. So now if you were to calculate the bond energies, hydrogen has a hydrogen-hydrogen single bond, chlorine also has a chlorine-chlorine single bond, and HCl, since we have 2 molecules of HCl, that means we have 2 hydrogen and chlorine single bonds. So basically, if you were to now calculate, the bond energy of reactants would consist of 436 and 242, and for products, it will be minus 2 times 431. And if we were to calculate this now, so 436 plus 242 minus 2 times 431. In that case, we get minus 184 kilojoule per mole. That means it's an exothermic reaction. The answer is B. Moving on to question number 14. Under certain conditions, nitrogen reacts with oxygen to form N2O. Again, the reaction is given. It's an equilibrium reaction. What is the activation energy of the reverse reaction? So whenever it's the reverse reaction, the products are now the starting point. It's the starting point for the reverse reaction. So in that case, again, activation energy would be calculated from the starting point to the peak. So the height that we are looking for is this red arrow. So now how would we calculate the height of this? Well, for that, we need this value, which was the total height, and the previous enthalpy change, because we can immediately see that if I subtract 164 from 447, I get the length of the red arrow, the new activation energy. So in that case, activation energy would be 447 minus 164. In that case, 447 minus 164 gives us 283, and it's an activation energy. It must always be positive or endothermic. Question number 15. Physical changes and chemical changes can occur in substances. Which process describes a chemical change? In a chemical change, it's generally permanent. A chemical reaction takes place. Reaction occurs. Therefore, we will find a product. A product that's chemically different. So if you look at the different scenarios presented, covalent bonds in methane molecules are broken. So in a methane molecule, we have these covalent bonds between carbon and hydrogen, and if we break them down, we end up with carbon plus 2 molecules of hydrogen. We see that our reactant and products are completely different chemically. So because of that, that means A must be the answer, but what about the other options and what's wrong with them? Intermolecular attractions between water molecules are broken. This occurs when we're going from a liquid to gas. Intermolecular forces are being overcome or broken at that stage, or basically during any state change, the intermolecular attractions are being broken. Now we know that state change is always a physical change, so that means B can't be an answer. Ionic bonds in sodium chloride lattice are broken. It's the same logic as the previous one. We had Na plus and Cl minus with a bond between them. Think about it in terms of sodium chloride dissolving in water. Sure, the lattice is broken, but the sodium and chloride ions still exist. It's not like the composition of the ions are changed in any way, or it's not like we are getting sodium metal and chlorine gas as our product. So again, C is wrong because of that. And for D, the manufacture of brass from copper and zinc, this is a mixture, as we already discussed. So mixtures are not chemically different, rather they share an average of the same chemical properties from the elements they're made. So that means D is again not correct. Number 16. Octane C8H18 is a hydrocarbon. When octane is mixed with an excess of oxygen, no change takes place unless energy is supplied. If energy is supplied in the form of heat or an electric spark, a change takes place quickly. The products of this change include carbon dioxide. Which part of this description shows that the change is a chemical change? So since we already discussed in the previous question, any chemical change will produce a product that's chemically different. Now, octane, which was C8H18, is definitely different from carbon dioxide, which is our product in this case. So the fact that carbon dioxide is produced is the reason why it's a chemical change. A, which says octane is a hydrocarbon, doesn't really make any sense in this case because it's irrelevant. No change takes place unless energy is supplied. This is not a way of determining whether it's a chemical change, because think about melting and boiling. Those processes also require heat, but they are only state changes and thus physical changes, not chemical. The change takes place quickly. That is again not necessary, because some reactions can be very slow but they will still be chemical reactions, and then some physical changes can be very fast and they'll never be chemical changes. Number 17. Hydrogen is used as a reactant both in the Haber process and in its addition to alkenes. Which row is correct? So the catalyst in the Haber process is iron. Nickel is used for the production of margarine. Basically when we add hydrogen to alkenes. And the product of addition of hydrogen to an alkene will always be an alkene. In that case, the answer is A. Basically, if you have your alkene, the double bond will disappear and hydrogen will attach to the carbon from the two sides. So that means it must definitely be an alkene. Number 19. Which statement is correct? Well, this should be number 18. Which statement is correct? A base will react with ammonium salt to produce a gas that turns damp blue litmus paper red. This is the other way around. It should have been damp red litmus paper blue, because when a base reacts with an ammonium salt, the products are, if you write it, base plus ammonium salt The products are a new salt plus ammonia, NH3, plus water. Now, ammonia is an alkaline gas. And since it's an alkaline gas, it will definitely turn our litmus paper blue from red. And then if you look at B, adding a base to an acidic solution will increase the pH of the solution. Acids generally have pHs ranging from 1 to 3 if they're strong. So when we add a base, let's say a neutralization reaction doesn't take place. Even then, the pH, let's say if we started at 2, will definitely increase to a new number because of the addition of bases, because bases have a high pH compared to our acids. So that is why B makes sense. It could be correct. Let's look at the other options. Aqueous sodium hydroxide is an alkali but not a base. All alkalis are bases, but not all bases are alkalis. Since sodium hydroxide is soluble, it is an alkali and also a base. And then in a neutralization reaction, a base donates a proton to an acid. Rather, it accepts a proton. The acid is the substance that donates a proton. So this should be number 19. Aqueous bromine is an equilibrium mixture. We have the reaction given to us. So bromine reacting with water. We have OBr minus ion, Br minus, and H plus ions. Now the information given is aqueous bromine is orange in color. The species on the right hand side of the equation are colorless. The changes are made to 3 separate portions of the equilibrium mixture, which row shows how the color of the mixture changes when a small amount of each substance is added. So equilibrium will shift depending on which concentration has increased. So if concentration of a certain product increases, my equilibrium will shift to the other side to compensate that increase, or to basically reduce the increase of that substance. So if you look at the first one, adding sulfuric acid. So sulfuric acid will provide H plus ions. So in that case, this concentration will increase. So since the product concentration has increased, as per Le Chatelier's principle, my equilibrium should move to the opposite side. It should move to the reactant side. Now, what do we have in the reactant side? We have bromine, and bromine has an orange color. So since equilibrium shifts to the reactant side, we will have more bromine in our equilibrium mixture. As a result, it will turn darker orange. Now, adding solid sodium bromide. Now, sodium bromide is soluble. So when you add it to the mixture, it will dissolve. And once it dissolves, it will release Br minus ions. Now, once it releases Br minus ions, again, if you look, the concentration in the product side has increased. So my equilibrium again shifts to the left-hand side, the reactant side. Again, the bromine concentration increases. So the solution turns darker orange. And lastly, adding water. Now, when you add water, we see that it's in the reactant side. Now, if you add water in the reactant side, then obviously it will go in the opposite direction. So in that case, the amount of bromine in my equilibrium mixture will decrease. That will force the mixture to become a paler orange. In that case, the answer over here should be B. This question is simply an application of Le Chatelier's principle. And then number 20. Lime water is aqueous calcium hydroxide, CaOH2. Which statement about lime water is correct? It has a pH below 7. That is not the case. It's an alkali, or a base at the very least. And bases will have pH above 7. It gives a blue-green color in the flame test. That is, again, not correct. Calcium ions give an orange-red color in the flame test. It reacts with ammonia to form an ammonium salt. So calcium hydroxide is a base, ammonia is a base. Two bases don't react together. So that will again not work. And then it turns yellow when methyl orange is added. So methyl orange is an indicator, and it has two colors. It has red and yellow. So it gives us a red color for acids, and it gives us a yellow color for neutral and alkalis. In that case, since calcium hydroxide is a base and alkali, that case the answer for 20 is D. Moving on to question number 21. Which definition of a hydrated substance is correct? So a hydrated substance is basically a salt that contains water of crystallization. Water of crystallization. And in our syllabus, the two main salts with water of crystallization that we learn is copper sulfate, which contains 6H2O, and cobalt 2 chloride, which contains 5H2O. So if you look at the options over here, a hydrated substance is a soluble ionic compound such as barium sulfate. Barium sulfate is insoluble, so that statement is wrong. A hydrated substance is an ionic compound that contains no water. That is again wrong. It must contain water of crystallization. A hydrated substance is one that is chemically combined with hydrogen. That is again wrong. It contains water, not just hydrogen, so H2O. And if you look at D, a hydrated substance is one that is chemically combined with water. This statement is correct. So the answer is D. Moving on to question number 22. A solution of sodium carbonate is added to tap water. A white precipitate forms. Which ion present in tap water causes the precipitate to form? Now, since it's a solution of sodium carbonate, so Na2CO3 in its solution would exist as Na plus and CO3 2 minus ions. So now if we try to recall the solubilities of group 1 salts, we would know that group 1 salts are all soluble. So any salt that would be produced by an anion reacting with sodium would automatically not form a precipitate and thus be wrong. So if you look at chloride and sulfate, that's automatically wrong. And when we think of carbonates, our carbonate ion over here, again, group 1 carbonates are soluble. So if that is the case, potassium, which is also from group 1, when it bonds with potassium carbonate, would again just form a soluble salt. So that would not give us a precipitate. Whereas magnesium from group 2 carbonates are generally insoluble. So in that case, B is the answer. Magnesium carbonate would be produced, and that is our white precipitate in this question. Moving on to question number 23. The table shows the number of electrons in one atom of each of the elements W, X, Y, Z. So W has 9 electrons, that means it must be fluorine. X has 15, so that's phosphorus. Y has 19, so that's potassium. And Z has 35, so that means it's bromine. All of these are directly available in the periodic table. So since F, fluorine, and bromine are from the same group 7, we can read that W and Z are in the same group, so that must be the correct answer. But let's look at the other options as well. X is a metal, X is phosphorus, which is a non-metal. X and Y will form the compound X3Y. So potassium and phosphorus would form an ionic compound, which would be which would be due to the K plus and phosphide ions, since the charges follow the crisscross method. In that case, the compound we would get is K3P, which would mean it's Y3X, not X3Y. So this is wrong as well. Y is a non-metal, Y is potassium, and potassium is a metal. Moving on to question 24. Which statement about group 7 halogens is correct? Bromine consists of Br2 molecules at room temperature and pressure. This is fine, so it's probably the answer. Let's look at our alternate options. Iodine will displace bromine. This is wrong because iodine is less reactive, so it won't displace bromine. Halogens become darker in color as the relative molecular mass increases, not decreases. As we go down the group, the halogens become darker. That is true. So as we go down the group, the relative molecular mass should increase instead of decreasing. Halogens become more volatile as the relative molecular mass increases. Now, volatility is the ability to vaporize. Ability to vaporize. Now, as we go down the group, the number of electrons increases, so intermolecular force of attraction also increases. Intermolecular force of attraction increases. Now, due to this increase in intermolecular force, that would indicate that my compound will require more energy to vaporize. As a result, halogens become less volatile as the relative molecular mass increases. Number 25, aircraft manufacture requires a metal that 1 has a relatively low density, 2 is resistant to corrosion. Which properties apply to aluminum? Well, if you look at 1 as a relatively low density, aluminum is a metal with low density, so number 1 is correct. And then 2, resistant to corrosion, aluminum has a layer of Al2O3, aluminum oxide, and aluminum oxide is insoluble. This insoluble layer, which is also very unreactive, not as unreactive, but it's insoluble, also behaves as a protective shield for our aluminum. So as a result, it is also resistant to corrosion, because this insoluble layer prevents water and oxygen to come in contact with the aluminum metal. So in that case, A should be our answer. Let's look at number 26, which diagram represents the structure of an alloy. So alloy is a mixture of metals. So we can expect to see different sizes of cations in our compound, or sorry, in our mixture, or in the structure of an alloy. In that case, if you look A, it's just all the cations regularly arranged. This is actually just the general structure of any solid, or in this case any solid metal. And for B, we see that there are cations of different sizes, so that would indicate that B is our answer. Let's look at C. C is just diamond or silicon oxide, depending on what they are trying to show, and D is just graphite. So none of these are the answers. Number 27, a small piece of metal is added to a large beaker of water. A vigorous reaction occurs. When the reaction stops, a few drops of litmus are added to the solution. What is the metal and which color is the solution after the litmus is added? Now, it is a metal and water reaction, so regardless of which metal it is, it will form a metal hydroxide, MOH2, and the hydroxide is an alkali. So the litmus paper should turn from red to blue. So the color we would observe at the end is blue. So that means red is not an option. And as for the metal, it said that a vigorous reaction occurred. And since both of our metals are from group 2, reactivity of metals down the group, reactivity increases for group 2. So for group 2 metals, reactivity increases down the group. So between calcium and magnesium, calcium is below magnesium in group 2. As a result, it will be more reactive, and hence the reaction with calcium will be more vigorous. In that case, A is our answer. Moving on to question number 28, which statement about corrosion of metals is correct? A barrier method is needed to prevent the corrosion of stainless steel. Stainless steel is already quite resistant to corrosion, so the barrier method is not required. Iron corrodes to produce hydrated iron 1 oxide. It should be iron 3 oxide. Sacrificial protection uses a less reactive metal attached to the metal object. It should be more reactive, so that the more reactive metal would react in place of the iron. That is the whole purpose of sacrificial protection. And for D, when corrosion occurs, the metal loses electrons to become positive ions. When corrosion occurs, the metal is basically reacting with water and oxygen. So yes, when metals react, they do lose electrons to form positive ions. So the answer should be D. The list for number 29 shows the position of metal X in the reactivity series of metals. So we have sodium, aluminum, iron, X, Cu, and silver. Which methods could be used to extract metal X? Number 1, electrolysis of solid metal oxide. Now this solid metal oxide can't be electrolyzed because electrolysis only works for molten or aqueous. So since it's a solid, the ions aren't free to move, so electrolysis won't take place. So 1 is wrong. Heating the metal oxide with carbon. So since X is below iron in the reactivity series, and since iron can be reduced by since iron oxide can be reduced by carbon to extract iron, X will also react similarly. So the metal oxide of X can also react with carbon and reduction will take place. So we will obtain the metal X. So 2 is fine, and then heating the metal oxide with copper. Now X is more reactive than copper, as we can see from the reactivity series. So copper won't be able to displace the metal from its oxide. As a result, number 3 doesn't work either. So in that case, the answer should be C, 2 only. All right. Question number 30. Which statement about natural sources of water and the domestic water supply is correct? Chlorine is used to remove tastes and odors. This should be carbon. So that is wrong directly. Rather, chlorine is used to kill any bacteria present or microbes present. So this is carbon. Metal compounds from detergents can deoxygenate natural sources of water. It's not metal compounds, rather it's the fertilizers. The fertilizers that dissolve in water and run off to the water bodies, because those would cause eutrophication. This point is basically referring to eutrophication, where the growth of algae is promoted due to those fertilizers, and those algae end up using the oxygen that otherwise fishes would have used. All right. And in D, it's stating photosynthesis provides the oxygen needed for aquatic life in natural sources of water. In photosynthesis, plants use glucose and not glucose. They use water and carbon dioxide to produce glucose, C6H12O6 plus O2, and if we balance this, there's just a 6 over there and a 6 over here. So these are the products, and if you look at the products, glucose and oxygen is produced. So yes, C is correct. And then if you look at D, sedimentation removes nitrates. Nitrates are soluble salts, so sedimentation wouldn't work. Sedimentation would only work for insoluble substances. Number 31. Some compounds that can be used as fertilizers are listed: ammonium nitrate, potassium phosphate, and sodium nitrate. If we write down the formulas for all of them, NH4, NO3, KNO3, K2, phosphate, so PO4, K3PO4, phosphate is 3, and then sodium phosphate, Na3PO4. So now let's look how many of these elements are present in each of the compounds. So ammonium nitrate contains nitrogen and neither phosphorus nor potassium, so that's 1 and 1. Potassium nitrate contains potassium and nitrogen, so that's 2. So in that case, we don't even have to look at potassium phosphate and sodium phosphate. We can directly say that the answer over here should be B. Moving on to number 32, which compounds are in the same homologous series? So either all of them are alkanes, carboxylic acids, etc. So let's look. So in option A, CH3, CH2, CH2, and CH3, this would be an alkane, butane to be specific. If we look at the next one, CH3, CH, CH, CH3, this would be butene. Now, how do we identify this? Notice the difference. Over here we have CH, over here we have CH2. Generally, in a structural formula, if you see that there is a CH in between, that would probably indicate that there is a double bond present. Now, you can draw out the structure just to be sure, but this is the case over here. And then if you look at the other one, CH3, CH, CH3, and CH3, this would be a branch structure. If we draw this out for convenience, H, H, and another H like this, then there is a hydrogen, CH3, CH3, and then another CH3. So this would be 2-methyl propane. So this is again an alkene, a branched alkene. So since we have two alkenes and one alkene, A wouldn't work. Let's look at the other options. So CH2, CH, and CH3. Again, if you look at this part, we have a CH, and usually at the ends, we know that we'll probably have CH3 if it's an alkane, but over here we have a CH2 at the terminal position. So that means this must be an alkene, so it's propene to be exact. And for the other one, CH3, CH2, CH, and CH2. Again, this is definitely an alkene. So 1, 2, 3, 4, that must be butene. And then the last one, CH2, CH, CH2, CH3. Now again, terminal position has CH2. That would indicate that this is an alkene. So in this case, this would be butene. So we can see that all of the compounds in this option are alkenes. So that would probably mean that B is our answer. Let's look what's wrong for the other options. So in C, we have CH3, CHOH, CH3. This is an alcohol propan 2-ol to be specific, since the OH group is present in the middle. If you draw it out, it would look something like this. So you have your OH and H and basically CH3 on the two ends. If you look at the next one, CH3, CH2, CH2 and OH, this is just propan 1-ol. And then the last one, CH3, CH2 and COOH, this is propanoic acid, a carboxylic acid. So now if you look at the last option, in our last option, what do we have here? CH3, CH2 and CH3, this is just propane. We have CH3, CH2, CH2 and CH3, that is butane. And then CH2CH, we have CH2CH in our terminal position. That means this must be an alkene. So 1, 2, 3, 4, 5. So that means this is pentene. So in that case, B is the correct answer. Moving on to question number 35. A chlorine atom can replace a hydrogen atom in a molecule of butane, CH3, CH2, CH2, CH3, to form chlorobutane. Let's actually draw butane to make things easier for us. So this is the molecule of butane. Let's give the hydrogens. So the question is, how many different structural isomers of chlorobutane can be formed? So chlorobutane is formed when one of these hydrogens is replaced using a chlorine. So now we have to check what are the positions of chlorine that can give different structural isomers. So let's say this 1, 2, and 3. All three of them at the end of the day represent the same structure, because if I give a chlorine over here or here or here, at the end of the day, if the rest are hydrogens, it's still just CH2Cl in my structural formula. So it's not changing anything. So this part would represent one structural isomer. Now if you consider the other positions, for the other ones, if we look at this part, if we replace a chlorine over here or over here, again it's the same idea. Whether it's above or below, it doesn't make a difference. At the end of the day, it represents the same structure. So again, that's 1 and 1 for the time being. And now if you go to the other side, hydrogen and hydrogen, if you replace both over here like this is hydrogen again we notice that it's the same structure as before, just flipped. So it's not a different structural isomer. And finally, if you go to the extreme end, it's again the same as the first structural isomer. So the conclusion is we have 1 plus 1, 2 structural isomers over here. So the answer is B. Now some might wonder that why aren't we considering structural isomers of butane, for example 2-methyl propane. That is mainly because the question itself specified that we are using a molecule of butane. So we aren't thinking of isomers in terms of the branches of butane. All right. So this was probably 33, this will be 34, and this will be 35. So which statement about organic compounds is correct? Each molecule of propan 1-ol has one OH group and each molecule of propan 2-ol has two OH groups. That is definitely not the case. Both molecules have only one OH group. Octane and decane are in a homologous series with the general formula CnH2n. So octane and decane are alkenes and the general formula for alkenes is CnH2n plus 2. The ester butyl butanoate has 8 carbons in each molecule. So the butyl part would be for butanol, so that has 4 carbons, and the butanoate part would be for butanoic acid, that has also 4 carbons. So 4 plus 4 will give us 8 carbons. So C is the answer. Let's look at D. The structure of the functional group in a carboxylic acid is COOH. Now they got it correct when they said COOH. However, the way they've shown the bonding, that is wrong. It should be C double bond O, single bond O, single bond H. This is the correct functional group. Moving on, the displayed formula of two organic compounds are shown. So we see that one is an alcohol with 1 carbon, so that's methanol. And 2 is an ester because of this functional group present, CO and O, and instead of an H we have a carbon. So this part has 1 carbon and it's bonded with the double bond oxygen. So that would indicate that this was the carboxylic acid. So we can see that this is methanoic acid. And this one we have 2 carbons, so this one is from ethanol, the alcohol. So methanoic acid and ethanol would form the ester ethyl methanoate. So now we have the names of the required compounds. If you look at our options, compound 1 is methanol, and compound 2, as we already determined, is ethyl methanoate. So the answer should be C for this one. An incomplete equation for the reaction of propane with chlorine is shown. So C3H8 plus chlorine, C3H7Cl plus X. So since one of the hydrogens is replaced with chlorine, X is simply HCl. A student writes 3 statements about this reaction. The activation energy for this reaction is provided by ultraviolet light. This statement is correct. One of the important requirements of this substitution reaction is the presence of UV light. C3H7Cl has 2 different structural formula. So if we draw that C3H7Cl, the chlorine could be in this position, that would be 1, or it could be in the middle. That would be its second position. So that indicates that there are only 2 structural isomers. So 1 and 2 are correct. And X is an acidic gas. X is hydrogen chloride. So that means it is an acid. So 3 is also correct. So the answer for 36 is A. Moving on to number 37. Polymer X is an addition polymer. The monomer used to make X is but1-ene. Polymer Y is a condensation polymer. The monomers used to make Y are CH2, CH2, OH on the 2 ends. So this is ethane diol. And for the other one, we have 1, 2, 3 carbons, and we have carboxylic acid groups on both ends. So that's propane dioic acid. So ethane diol and propane dioic acid. So these would form a polyester, an acid, and an alcohol always form an ester. So any option that mentions polyamide is wrong. So we look at B and D. Now, how do we determine the repeat unit? We simply draw a but1-ene molecule. So if we draw a but1-ene molecule, it would look something like this. And generally for drawing addition polymers, it's suggested we draw it in the form of an ethene molecule. So that is what we're trying to follow over here. So if that is the case, we would write C2H5 for the remaining extension, a hydrogen. And now in an addition polymer, the double bond one of the double bonds breaks down, so we have extensions on both ends. So this would be the repeat unit. Now if we were to check, we are looking for the presence of a C2H5 in the structure as per our format. So if that is the case, we see that D has that, but B doesn't. B is actually the repeat unit if we had used but 2 in, not but 1 in. So the answer for 37 is D. Let's look at number 38. Compound X decolorizes acidified potassium manganate. That means compound X is oxidized. So that is alcohol according to our syllabus, or that is usually an alcohol according to our syllabus. Compound X has the empirical formula C2H5O. Some possible structures of X are shown. So let's just go through them one by one. So in 1, we have 2 carbons, but we have 1, 2, 3, 4, 5, 6 hydrogens. So 1 doesn't work. Let's look at number 2. In number 2, we have 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C4, H10, and O2. If we simplify this, we get C2, H5, and O. So 2 is correct. Now, if you look at 2 and 3, you will notice that they are just structural isomers of each other, because the OH group is once present in the terminal position and then once inside or once with the second carbon. So if 2 is C2H5O, then 3 must also be C2H5O, and their reactivities are also the same. And for number 4, it's a carboxylic acid which doesn't get oxidized, so it won't react with potassium manganate. So in that case, our answer for number 38 is C, 2 and 3 only. Moving on to number 39, the diagram shows a chromatogram. The RF value, which spot has an RF value of 0.75. So RF value is distance traveled by the dye divided by distance of solvent front. This is the main formula for the RF value. So now if you were to apply that accordingly, so we can easily see that since it's 0.75, it must be either D or C. Thinking about B and A would be a waste of time, because the distance has to be at least greater than 50%. So let's measure the distance of the solvent front. So it's from 1 to 9. If that is the case, it's 9 minus 1. So the distance for the solvent front is 8. Now let's check for C first. So it's 1 to approximately 7. We can take a 7. So that would be 7 minus 1. That's 6. So now if we were to find the RF value, it would be 6 over 8, which is 3 over 4, which simplifies to 0.75. So in that case, C is the correct answer. A lot of students will look at D, align it with the fact that it's 7.5 on this scale, and say that D is the answer. However, the D can't be the answer, because the solvent front didn't travel from 0 to 10. Rather, it traveled from 1 to 9. So we need to measure the distances according to that. Finally, in question 40, a student does 2 experiments. In experiment 1, ammonium carbonate is reacted with dilute hydrochloric acid. In experiment 2, ammonium carbonate is heated with aqueous sodium hydroxide. In each experiment, the gas evolved is tested with damp blue litmus paper and damp red litmus paper. So the setup is given to us. Which row correctly shows the color of both pieces of litmus paper at the end of each experiment? So when dilute hydrochloric acid, HCl, reacts with ammonium carbonate, NH4 to CO3, our products are ammonium chloride, carbon dioxide, and water. Won't bother balancing the equation because it's not required in this question. So carbon dioxide is an acidic gas, so we can expect our litmus papers to be red. So the red one will stay red and the blue one will also become red. So experiment 1, our expectation is red. And for experiment 2, sodium hydroxide, an alkali, is reacting with an ammonium salt, and when alkalis react with ammonium salt, they displace the ammonia. So what they end up producing is NaOH plus NH4CO3. So our products will be a salt, so Na2CO3 plus ammonia gas plus water. So the ammonia gas is alkaline, and alkaline gases will turn damp red litmus paper blue. So in that case, the answer for this one is red and blue, so the answer should be C. And that is the entire paper.